this is about TIAM Grantham. But TIAM is the Times Integrated Assessment Model, and I'll just describe quickly what TIAM Grantham is in a second. Background of TIAM, as probably all of you know, actually, is that it was developed under the IEA ETSAP program. Original, sorry, I just put my laser pointer on so you know where I am. Yep, the origins of TIAM are from some global models used by the IEA and also the US EIA. Times Integrated Assessment Model, then it kind of dives into acronym hell. The Integrated Markal EFOM system, some of you will have heard of Markal, the Market Allocation Model, and then EFOM, Energy Flow Optimization Model. So someone obviously got a bit overly excited about their acronyms. There are many versions of TIAM. We work with and have worked in the past with UCL, with their TIAM model. We're aware of the TIAM ECN model. We have a version, TIAM Grantham, and then Amit Kanudia, one of the sort of original developers of TIAM, runs TIAM World. They're all basically the same. They have different regional splits, sometimes different technological representation. Some of them have more updated or different assumptions on things like fossil fuel supply cost curves and so on and so forth, but they all use the same essential modeling philosophy, which I'll describe in a second. What does TIAM do? Well, you know, kind of energy modeling or emissions modeling 101. All of you probably do this, but we start with a storyline, which is generally using exogenous variables like population, dynamics, technical progress, and so on and so forth. In the past, that storyline was then converted using a CG model, Gemini A3, into different drivers of things like GDP, sectoral value added, so industry value added, services, and agriculture, and so on. So, you know, in a sense, this gives us a view of what we need services and energy for going forward into the future. This then translates into demand for energy end uses, so demand for buildings, transport, industrial energy end uses, according to these elasticities that we have. So, you know, as the world gets richer, how much more energy does it need to transport itself? How much more does it need to heat and cool households and commercial buildings? How much more industrial manufactures does it need, and so on? That then kind of takes us into the green part, which is once we have these end-use demands of energy across different sectors, we then have assumptions on the different technologies and fuel sources, energy sources that are available to meet those demands. And then you have within that a sort of implied set of mitigation options. So a mitigation option will be replacing coal-fired power with solar power, for example. You also have carbon removal options. We only used to have bioenergy with carbon capture and storage. Over the last 4 or 5 years, we've coded in different representations of direct air capture technologies, for example. We then have the sort of price quantity equilibration that's quite similar to what Jon described for GCAM. And then TIAM also does have a climate module. We tend not to use it so much. We tend to use what we consider to be better reduced climate models from different groups. But yeah, I'll show a quick slide on the climate module in a second. We have lots of different available mitigation options. Energy and technology substitution, like I just described. We have demand reduction. We have assumed elasticities of demand for energy responding to price increases or falls in energy costs. We do have some specific methane and nitrous oxide options, but again, we don't really use those. We tend to couple TIAM, the energy system part, with other models which have more detailed representations of these other gases, although we are developing TIAM to have a better representation of these gases. We have sequestration of CO2 and biological absorption of CO2 as well. So all of the sort of main options that allow us to simulate pathways to sort of net zero and net negative emissions. We have 15 regions in our vintage of TIAM. I think some groups have quite a lot more regions, but these are the sort of core 15 regions that we have. We have 5 end-use sectors, so we split buildings into residential and commercial buildings. We've got an industrial manufacturing sector, which is split into the main sort of industry sectors: cement, iron and steel, pulp and paper, and so on and so forth. We have an agricultural sector in terms of its energy demand use rather than the nitrous oxide and methane emissions from it. We have a transport sector as well. Then we have different energy supply sectors, and we have interregional trade in fuels and carbon permits. We have a detailed energy system representation, which is very similar to GCAM, so I won't dwell on that. Just to repeat, though, that we have these sort of 5 categories of end-use sectors: industry, agriculture, commercial and residential, buildings, and transport. The solution objective is basically least cost optimization or welfare maximization. So you basically have a sort of supply curve of different, this takes the electricity sector as an example. You have a supply curve of different electricity sector technologies, and then you have a demand curve of demand for electricity. The model will work out the consumer and produced surplus, the combination of those being the overall sort of welfare, and it can maximize that welfare. You can run the model as well without the elasticity of demand assumption, and that basically ends up with then a sort of least energy system cost solution rather than a welfare maximization solution. We have a climate module. I'm not a working group 1 scientist, but basically it takes emissions, calculates concentrations and forcing, and then temperature with some coupling of atmosphere and ocean systems. And TIAM can represent a range of policy instruments, not with the sort of granularity we would like, but we've got predominantly, I guess, we specify either a carbon price or a carbon emissions constraint. So, we can put a carbon price pathway into different regions in the model or across the world as a whole. We can do the same with carbon emissions constraints, so we can implement simulations of NDC targets in 2030, net zero targets in 2050, 60, 70, and so on and so forth. That's all very easy and standard. Then we can also do other things which are a little bit tricky, but things we do all the time. So we can specify things like minimum and maximum capacity factors on fossil power generation. That's helped us to look at things like sort of trying to phase out coal, in line with historical patterns of energy system change, for example, by putting minimum capacity factors on it, which decline slowly over time. We've done a paper with BC3 colleagues and others recently looking at subsidies on particular technologies through adjusting their costs. So that's helped us to examine things like post-COVID-19 recovery. We've put constraints on the availability of particular technologies. You will have all seen those charts in AR5 about sort of no nuclear or no CCS scenarios, and we've done a lot of stuff like that as well. We can also put constraints on, the share of renewables. We put frequently constraints on the growth rates of particular technologies, and that allows us to look at sort of what if scenarios, what if technologies don't scale to the rate that we hoped they would. And then we can also do things like interregional emissions trading. So we can look at sort of the costs of mitigation with and without carbon trading, for example. Key policy relevant questions. So, what's the cost of delay in mitigation? That very sort of common question. We can calculate the energy system cost or the welfare loss as a share of baseline GDP, and we can express that, in particular years or as a present value discounted over the century. Our model runs till 2100, by the way, in 10-year time steps, although we can make adjustments so that we can run in 5-year or single-year time steps in the near term, which is what we've been doing increasingly in the recent past. We can look at different feasibility indicators of global and regional mitigation, cost of mitigation with and without carbon trading, also things like, what's the sort of implications of exploiting particular fuels or technologies, and we did something on shale gas, implications of delay or unavailability of technologies. We've looked increasingly at running TIAM in a stochastic mode, so we can look at things like how would you mitigate in the 2020s if you had an uncertain availability of CDR in the post-2030 period. Done some big studies on direct air capture, some studies looking at what if we can't break with historical trends of energy system transitions, and what does that mean for the feasibility of different targets. implications of lowering demand for energy, and what happens if you put lots of new advanced technologies in. The technology richness of TM allows us to do that. And then we can sort of weigh up technologies against each other and say, look, if the costs of one technology fall, like renewables, what does that do to the contribution of CCS and the value of CCS in mitigation scenarios? We have no particular direct SDG modules in TIAM, but we can look at some sort of health related SDG aspects by looking at the use of solid fuels in building. We'd need an off-model calculation of local air pollution for that, though. We can do all sorts of analysis on affordable and clean energy. We can do analysis on the macroeconomics of the transition, and we do have some internal afforestation representation in TM, but again, it's not something we use very often. That's it from me.